So hierarchical methods, earlier we talked about partitioning. The partition method that we introduced so far all partitions every data points. So the noises are also being clustered. When you compare the PAM and the K means, K means are more susceptible to outliers because it computes the mean. The Meadows methods are less so because it has a representative observation. The hierarchical clustering does not ask you to provide a K. The K that you can decide after the clustering are formed. The hierarchical clustering produces a set of nested clusters organized as a hierarchical tree. So earlier we have this little example here. 1 and 3 are the closest, so they first formed a cluster, and then 2 and 5 formed a cluster. Then we continuing adding the points to the cluster, closest cluster, and form bigger clusters. And this bigger cluster covers the smaller clusters. So you end up with a dendrogram like this, where when you have a dendrogram like this, you actually can decide where to cut. If you need 2 clusters, you will cut right through here. So you will have the number 6 being one on its own cluster, and the rest of the things are another cluster. If you need a cluster, 4 clusters, you will cut over here. That gives you lots of flexibility in terms of how many clusters that generates for you. However, this algorithm is much more computationally expensive than the k-means. I think we talked about this. Hierarchical clustering, we can do it top down and or bottom up. The agglomerative method goes from bottom up. Divisive method goes from top down. So both of those algorithms use a dissimilarity or distance matrix, and we're going to look at how they work. The idea in either direction, whether you go top down or bottom up, it's merge or split one cluster at a time. So if you go from that direction, you do agglomerative, you add things into clusters. If you do the other direction, you do divisive, you split this large clusters into smaller clusters until that you have every data points in its own cluster. So we're going to look at Diana, the divisive algorithm first. Divisive is used less frequently, but I think the result should be the same. It's just maybe it's a bit more costly. So to do the division at each stage, the cluster with the largest. So remember, we do divisive. We start with the entire data set in one cluster. Then we choose where to split. So in this large group cluster, we find the most disparate observations, which is basically this data point in this cluster that's farthest from the other observations. We will use that data point as the splinter, as the seed in the splinter group. And then the algorithm will reassign the observations so that observations closer to that splinter seed will be grouped into that group. This causes one cluster to be split into 2. And then we pick, again, among existing clusters, the cluster with the largest diameter. again, there are multiple definitions for largest diameter that could be used. One example being the maximum dissimilarity between any 2 points that measures the diameter, and we pick that point again to see which point is the most disparate observations, and we use that as a seed, assign observations within this cluster to these 2 different groups, and continuing split until we have at the bottom layer we have every cluster holds 1 example. Agglomerative clustering algorithm does similar things in different direction. So first we compute the proximity matrix, which is a n by n matrix that tells the distance between the 2 data points. So first we assume every data point is 1 cluster. Then we try to merge. In the data matrix, we should be able to tell which 2 data points are the closest, and we merge those 2, merged into 1 cluster. Then we update this distance matrix. And we do, in that distance matrix again, find the 2 closest clusters, merge them, then do this repeatedly until every data point is in 1 single cluster. So as you can see, the key operation in this method is to compute the proximity or the distance between 2 clusters. And there's multiple ways that we can do that. And we're going to look at those shortly. So at the starting position, we have set of data points. When we have this proximity matrix, we have all the data points. And at a certain step that we have merged some, our data points becomes clusters. Again, here we should fill those matrix with the distance scores. When we found C2 and C5 being the closest, we want to merge those 2. When we merge, then we update the matrix. So when C2 and 5 are merged, then all the row and columns should be updated. I should also mention this should be a triangular matrix. So this or symmetrical matrix, that this value and this value is the same. So the distance between C1 and C3 is the same as the distance between C3 and C1. So the example illustrates that really the key here for this algorithm is to decide how to compute the distance. And there are multiple ways to do that. We can do between 2 clusters, we can find what they call mean distance, also known as single link. This is just the 2 data points that's closest. 2 data points in the 2 clusters that are closest to each other. Max, you can probably imagine, that's the 2 points belongs to these 2 separate clusters that are furthest apart from each other. And we can also do group average. We can do distance between the centroid. And you can use other fancier methods as well. I think the R methods that we used in our exercises allows you a number of different choices. Using those min max has a consequence, especially min max. The average and centroids often give you similar results, but mean can give you very interesting results. This allows you to do contingency-based clustering, as we're going to see here. So here we have those distance matrix. By looking at those numbers, we can see that P3 and 6 should be merged first because it has the smallest distance. And then after that, we should merge P2 and 5. And after that, we're going to see which point is the closest, maybe 4, 2, 3. So this is the closest. Oh, okay. Mean, so 2 and 3 is closer than 3 and 4. Therefore, 3, the third cluster is formed here. And then we include 4, then we include 1. So this creates a hierarchical clustering this way. The strength of the mean is because a look at the nearest neighbor, basically. So it allows you to create clusters that are not elliptical shaped, not all global shaped. But also it's not perfect. When you have the mean, obviously it's depending on one, the most closest to it, so it's sensitive to noise and outliers. When you have the original points like this, your clusters could look like this. When you cut through and find 2 clusters, and when you cut 3 at the level 3, you could have an individual cluster that look like this. Max or complete link, the initial 2 going to be the same because those 2 are really the smallest distance. We're going to group 3 and 6 together and 2 and 5 together. 3 and 6, 2 and 5. And then now we're looking at the maximum distance. So this, the group 1, 2 cluster now is this much distant because we look at the furthest. Therefore, I think 4 going to be included into cluster 1 first, right? And then 1 to that cluster, and then join the 2. So the max has, again, strength and weakness. It's less susceptible to noise and outliers. However, it tends to break large clusters with a smaller cluster that's closer by. That it also creates problems. Group average, and similarly, that you can compute the proximity based on the group average. Now we compare every data points to another data points in the other cluster. Therefore, your denominators has to be the size of cluster 1 times the size of cluster 2. So we have again a different sets of cluster result. The group average is a compromise between the single and complete link. Therefore, their strengths and weaknesses is all sort of averaged out. That's less susceptible, but also it has the bias of towards globular clusters. So those are the things that we have talked about, and the centroids and medoids, very similar ideas. I think this probably was from the next week's thing. Because H cluster is a hierarchical clustering methods that we used in R. I think this one shows you that you can actually cut at different places and get different clusters. So here we cut the tree at, we want to get 6 clusters. And here we can actually cut to get 2 clusters. And this cluster is really, really very small, only have 5 instances.